Okay, maybe we can get started. So welcome back, everyone. The first talk for this morning is by Alex Fink from Queen Mary University in London, though at the moment he's in Seattle, so he's very kindly agreed to join us, though it's very late in the night for him. And he'll tell us about connecting tropical intersection theory with polytope algebra in types A and B. Over to you, Alex.
All right, thank you, Pranav. And thank you all for coming. I do wish I was there, but yes, hello from Seattle. And so yeah, this is a talk on joint work in progress with, I see I got not only the date wrong, but the alphabetical order of my co-authors wrong as well. Chris Ure, Matt Larson, and Hunter Spink, which we hope will be on the archive this summer. This will not be the title. The title will have Delta-matroids in it. So this is a story whose combinatorics is about matroids and delta-matroids. So I will start with the matroid side of it. Probably a familiar object to many people who think about especially tropical algebraic geometry, because a matroid is the data you need if you have a linear space over a field, say, with the trivial valuation, and you want to compute its tropicalization. That is what I've given as a slogan here. The definition I've given is not the standard one you'll find first in most textbooks, but it's nice for our purposes. So I will say that a matroid on the ground type 1 through n is a certain kind of polytope. Namely, it's a 0, 1 polytope. It's got vertices in 0, 1 to the n, and its edges have to be parallel to these type A root directions. That's the type A of the title. That is EI minus EJ, vectors with a single 1 and a single minus 1. So each edge, you swap a single 0 with a single 1 because the edges are 0, 1 vectors. So I've got 2 polytopes on the slide. Both have vertices that are 0, 1 vectors of length 4. So these live in R to the 4, although they live in a hyperplane, so they're 3-dimensional. And you can see that the right one is not a matroid because the edge I've highlighted in red has direction E1 plus E2 minus E3 minus E4. I have to change 2 1s to 0s and 2 0s to 1s. So that's a bad edge. And the polytope on the left has no bad edge like that. So the green polytope on the left is a matroid. So that's the definition. What does it have to do with linear spaces, the slogan I started out with? Well, the usual definition that you're more, or one of the definitions you are more likely to see in a textbook or whatnot, will say that matroids are a certain kind of set system. There is an obvious bijection between 0, 1 vectors of length n and subsets of the set of numbers 1 through n. Namely, I associate with each set its indicator vector. That is my E sub capital S right here. And therefore, a matroid, as I've defined it, a polytope, can be associated to a set of sets, a set system, namely the set of all these sets that appear as its vertices. These sets are called bases. And a much more common way to define a matroid is in terms of these bases. A matroid is a set of bases, and they have to be sets that are close to each other in some way, given by the exchange axiom that corresponds to Steinitz exchange from vector spaces. I won't state it, but it's the translation of this condition on the edges that you can switch 1, 1 to a 0 and 1, 0 to a 1. So in terms of bases, we can say what the matroid is that belongs to a vector space. If I've got a vector space, I represent it as an image of a matrix. And then I look at which maximal minors of that matrix are non-zero, and those are my bases. In other words, which set of the rows in my matrix are a basis. So if I want to produce the matroid I had in the previous slide, where The only non-basis is this one here, 1 and 4. That means I want to take 4 vectors in K squared, where the only non-basis is the first and the fourth one. So I'll do them as row vectors, so I can use, the same vector 1 and vector 4, and then put non-parallel vectors in for the second and the third. So this is an example of a matrix which represents the matroid on the previous slide. If I look at which minors of this matrix are 0 and non-zero, I get the set system whose convex hull is the polytope in green on the previous slide. Okay, note that this green box at the bottom is an example. Not every matroid is represented by a matrix. Not every matroid actually comes from the geometry of a linear subspace over some field, and that will become important. Okay, so the other way that matroids, well, the way I said matroids are probably familiar to this crowd is that they let you tropicalize a linear space. I've given the definition of how you do that here in a slightly tricky to unpack way. So, okay, what is this? The Bergman fan, the tropicalization of the linear space, right? That's, if you have a linear space phi, its tropicalization is this Bergman fan. How do you get it? Well, it lives in the dual space to the matroid, which is a polytope. It has a lineality space, which is this all ones direction. I've written as the sum of all the xi, that's the all ones direction. So I mod that out. Once I mod that out, here's the support of the fan. The support of the fan is a certain part of the normal fan of the matroid. I look at all of the faces that don't have any single variable xi equal to 0. And the collection of normal cones to those faces in the normal fan is this Bergman fan, and that is the tropicalization of a linear space. So for the example, which I've drawn back here, there are 3 faces like this quadrilateral facing us. That no coordinate is constant 0 on that face. So I include the ray through that face in my Bergman fan. And then I have 2 more faces at the left and right on the back, these 2 triangles, this one and this one. Also no coordinate is constant 0 on those 2 faces. So I get rays through those 2 faces as well. And my tablet skills are not perfect, but you get a cell complex with 3 rays, and that is the tropical linear space that corresponds to this matroid. Okay. It's worth saying that you can also recognize matroids as certain Bergman fans or certain tropical cycles. Intrinsically, you could have defined them in terms of certain kinds of tropical cycles. They really are the fans that are degree 1 in tropical intersection theory, so it's reasonable to think of them as linear spaces. I won't be using this very much. I just include it to show that there are really many equivalent ways to define a matroid. This is Rota's cryptomorphism. Okay, so one very exciting development in combinatorial commutative algebra recently has been the exploitation of the Matroid Chow ring. So now that I've defined the Bergman fan, I guess I said half the definition of the Bergman fan, so I'll pop back for a moment. I said what its support was. I didn't say its face structure. I need to tell you where the rays are, which sets of rays make up a face. So that is this line I forgot to read. Sorry, at the bottom. All the 0, 1 vectors in the Bergman fan are rays, and every subset of those rays that generate a cone in the Bergman fan make up a face. So that at least defines a fan.
Hello,
I will leave it
Alex.
at that. Yes.
Sorry, just quick comment. So it'll be good if you clarify the theorem, this theorem ones a bit more, maybe elaborate. So tropical cycle and weights, people are familiar with weights, but just a tropical cycle is something people may not be familiar.
Fair enough. Yes, I will talk about this theorem more then. Thank you. Yes, this theorem, I included this theorem here really as to mention tropical intersection theory. I guess I should mention it more than offhand. So by a tropical cycle, it's sufficient to think a tropical variety, so a weighted balanced polyhedral complex, or a linear combination of these where the weights add if I have the same face twice. So if I have some collection of polyhedra, all the weights are 1. And what it means that its degree is 1 is that if I intersect it with a linear space, a tropical linear space, say the tropicalization of a line of the opposite dimension, in this case, I will have another tropical line. Well, by the tropical Bézout's theorem, the degree of the blue thing is the number of intersection points of the blue and the red thing. If the red thing is a generic translative tropical line here, there is 1 intersection point, so the blue thing has degree 1. So using tropical intersection theory in this way, you can say that tropical linear spaces have degree 1 in this tropical intersection theory. Thank you for the question.
Thank you. Thank you.
Yes. Good. So, tropical intersection theory, in that sense, will show up, well, in a way it shows up on this slide, but tropical intersection theory is essentially toric intersection theory. There is this presentation by Fulton of toric intersection theory using Minkowski weights. And so the Matroid Chow ring, I was in the middle of introducing, it can be defined as a Chow ring of a certain toric variety. So a toric variety associated to the fan, the Bergman fan, that I introduced on the previous slide. I haven't put the definition here because I'm not going to use the structure. If you've seen the construction, that's right. So you have a generator for each ray, then you quotient by a Stanley-Reisner ideal for the phase structure and a linear ideal for how the rays are embedded. But I won't need to use that. It's a certain Chow ring of a certain toric variety. That's the best way to define it in terms of what I have here. Now, what's exciting about this ring is that it behaves like the Chow ring of a complete projective variety. Now, if my matroid is representable, if my matroid comes from a linear space, then there's actually a projective variety which is Chow equivalent to this X Bergman of M. That is called the wonderful compactification of M. But if M is not representable, if there's no linear space, then there isn't actually a complete projective variety which has this Chow ring. Nonetheless, it has the properties which the Chow ring of a complete projective variety does. Which properties? Well, there are these 3 identified in this theorem. This ring A star of M always has Poincare ray duality. It has the Hard-Lefschetz property. It has the Hodge-Riemann relations. Again, I won't be using these precisely, so I won't spell out what they are, but these are a collection of positivity type statements in algebraic geometry that Jun Ha and others have called the Hodge package, and they are true for geometric reasons of complete projective varieties, say over C, but they also hold for all of these Matroid Chow rings. Question?
Yes, Jyoti. Jyoti has a question. Can you please unmute yourself and ask? They need to unmute it. Huh? Can you please unmute Jyoti? Oh, okay. She's unable to unmute upstairs. AB team, unmute, please.
You could type the question, I suppose.
Yeah, otherwise you can just type it. They will unmute you in shortly. They have heard it, probably. Yeah.
So yeah, the toric variety I have defined is not projective. And so even the realizable case of this theorem is using a fact I didn't say here, which is that if M is representable, then there is a Chow equivalence between this Chow ring of the Bergman fan and a toric variety that is projective. No, sorry, not a toric variety, a variety that's non-toric but is projective, the wonderful compactification associated to a linear space V that it comes from. So if M is represented by V, if V represents M, my handwriting is not very good. If V represents N, then there exists a projective variety which has the same Chow ring. And that explains the theorem. But if M does not have a vector space that represents it, then there doesn't exist a projective variety. Nonetheless, the ring has the properties that it would if there did exist a projective variety. So that's the magic part.
Sorry, just that the way you define a matroid, there is a lattice polytope underneath it, right? So that gives you a projective toric variety, but that's not what you are looking at here.
That's not the one I'm looking at, right?
Okay.
I took a subfan. Bergman is not a complete fan. I took a subfan.
Right. Okay. Yes.
That's right. Yes. Thank you.
Thank you.
That toric variety that you asked about, that will show up later, but at this point, yes, this is a non-complete toric variety, Bergman of M. And so, yeah, the theorem is, given this definition, the theorem is interesting when M is representable and extremely interesting, revolutionary when M is not representable. So, what is great about this theorem is that there are inequalities that come from the Hodge-Riemann relation. This tells you signatures of intersection pairing, so you can get positivity from that. And that was used to establish several combinatorial conjectures, which have been open for a long time, like this conjecture of Rota in 1971. That's the one from this paper that I cited. So there is this way to get geometric positivity statements from a ring which doesn't actually have a variety associated to it, just a matroid. And that is the kind of thing that I'm doing in my work in progress in a slightly more general setting. Okay. So, I guess the first thing I want to say is that really, in this paper in progress that I'm talking about, we do work in an actual particular projective toric variety. So the ambient variety is an honest to goodness toric variety. And instead of working in the Matroid Chow ring itself, we worked in this toric variety of this fan, sigma A sub n minus 1. So that's the complete fan belonging to a certain hyperplane arrangement. It's actually is one of these Bergman fans. So there's one Bergman fan which is complete, and it's this one. So this is the unique complete Bergman fan. And we look at its toric variety. So that is a nice projective toric variety. And well, it turns out all of the other Bergman fans are included, at least as groups, in the Chow ring of this toric variety. That is this fact at the bottom. you can take the Minkowski weight, this Bergman fan that I defined, and the set of classes you can get by multiplying by that is as a group an isomorphic image of the Matroid Chow ring. So for the purposes of this talk, the way we'll work with these positivity statements is not by using a Matroid Chow ring, but by using this particular permutahedral toric variety, at least in the type A half of the talk. So that's the type A half. Onto the type B half. So delta-matroids. What's a delta-matroid? Well, I said it's supposed to be a type B analog, so we change the type A root system to the type B root system and repeat the definition otherwise. So now we are looking at polytopes, which have vertices that are 0, 1 vectors, and the edges, well, there are a few types of directions, right? I can have edges parallel to the coordinate axis, EI, or in direction EI plus or minus EJ. So again, I've drawn an example and something that's not an example. Both of these have n equals 3. So they are subpolytopes of the cube, of the unit cube. And you can see the non-example in red has a long edge that goes between the point 0, 1, 0 and 1, 0, 1 or something like that. So there is an illicit direction of edge between these 2 points. So that's not a delta-matroid. But there's no such bad edge direction in this green polytope. So that is a delta-matroid. Parallel definition to the one I gave for matroid. And in a similar way, you can view it as a set system. In this case, the same thing. You look at the sets whose indicator vectors are in the delta-matroid, and you get this set system satisfying symmetric exchange. So I'm looking at this middle set system here. You can make that in exactly the same way as the matroid. So these are certain kinds of sets of subsets of 1 through n. But it's sometimes useful to also throw in extra elements, 1 bar through n bar, sort of representing sets or elements which are not present in my set, right? So if I have a set like 1, 2, maybe if n equals 3, and I have a set like 1, 2, I can represent it as 1 and 2 and 3 bar to encode that 3 is absent. So we get what's called an admissible set. And for some of the combinatorics, it's useful to keep track of these admissible sets. These are 2 very closely related ways to see these as set systems as well. So why are delta-matroids of interest? Some people like Coxeter combinatorics and generalizing one root system to others, but let's suppose that doesn't motivate you. Well, here are a few things that might motivate you. So they generalize matroids. Matroid basis polytopes are the way I define matroids. This is because the type A n-1 root system is a subset of the type B root system, so matroids are a special case. But there's another polytope associated to a matroid as well that is a delta-matroid, which is the set of all independent sets. An independent set is a subset of a basis. So if you take your matroid polytope and add all the coordinate-wise smaller 0, 1 vectors as well, you get something called an independent set polytope. And that's another example of a delta-matroid. So even if you only like matroids and not Coxeter things, you get 2 avatars of matroids here, which is potentially more combinatorially powerful. You have an analog of the representable examples I gave for matroids. In this case, the type BC the geometry is that you should have a 2n or 2n plus 1 dimensional vector space with a nice quadratic form on it, maybe a symmetric bilinear form or a skew symmetric bilinear form, depending on whether you are in Lie type B or C or D. If you have then a maximal isotropic subspace for that bilinear form, you do the same thing as I did in Matroids. You write down a matrix for this space V. You look at which of its maximal minors are 0 or not, and that will produce a delta-matroid. It is not quite as closely connected to the tropicalization, but there's a paper of Philippe Rincon which describes the relationship there. And I should say, actually, delta-matroids predate all of this Coxeter stuff. The Coxeter stuff was introduced by Borovic, Gelfand, and White in 2003, but delta-matroids were introduced much earlier by Boucher in 1989, and they have some purely combinatorial sources as well. So if you have matchings in a graph, or you have a graph in a surface, you can produce delta-matroids combinatorially that way. So that's one of the two objectives of this paper, is to do with delta-matroids some of the positivity that was done with matroids, parallels of these results that Junha and others have. The second sort of generalization that we want to make is to allow you to work in K-theory as well. And now we're kind of getting to the other part of the title, which is the connection between tropical intersection and polytope algebra. So, as I said, when we were talking about this tropical intersection theory is essentially toric intersection theory. So it is working in the Chow ring of a certain toric variety, a certain projective toric variety that you choose in such a way that both the tropical varieties you're intersecting are subfans of the fan you're working with. So that is all intersection theory, Chow ring. There are some computations in combinatorics that sort of suggested that it might be useful to have K-theory as well. For instance, in work with David Spire, I showed how to compute certain matroid invariants. The tup polynomial is one. Spire's G invariant. This is about enumerating the faces of a tropical linear space. And we showed a formula for these that used K-theory of Agrestinelli. Then in work with a graduate student, Amanda Cameron, we get a similar formula that was computed by counting lattice points. Okay, now counting lattice points isn't overtly K-theory, but I'm about to say that these kind of polytope computations are in fact isomorphic to K-theory. If you're used to association between lattice polytopes and line bundles on a toric variety, then counting lattice points is counting sections of these line bundles, and the linear relations between them are Rotendieck group type relations that you get in K-theory. So there were a few computations that suggested it might be nice to have a K-theory take on these computations as well. So Morelli in 1993 gave a presentation of the K-ring of a smooth projective toric variety. I have this in Terabang here because his proof had a flaw in the polyhedral reasoning that was found by Peter McMullen, but my co-authors Ayyer and Larson, together with Junha, have checked it and are convinced that actually the statement is okay, and so they will be publishing this soon. So this is a theorem that describes the K-ring of a smooth projective toric variety, and it describes it in terms of polytopes. So it is a ring that has also appeared as the polytope algebra of McMullen. So what is this? This is a ring generated by polytopes, or more precisely, by the indicator functions of polytopes. So the indicator function takes value 1 on points in the polytope, 0 on points not in the polytope. It's a function from R to the n to z. And if I have a collection of polytopes, these indicator functions, I can add and subtract them. I can form the group generated by these indicator functions. That's what I do here. I fix a fan, look at all lattice polytopes that are compatible with this fan in the usual toric way, so that the normal fan coarsens my given fan. And I look at the group generated by all of those indicator functions. So what kind of relations are there in this fan? Well, for instance, if I have a square as one of my polytopes, well, the indicator function of this square, say I cut it in two into this triangle and this triangle, well, I've double counted the line in the middle. So I have a relationship like that in this group of indicator functions. I take this group of indicator functions. I also quotient it by relations that correspond to translation. That is the thing I've called I bar of sigma. That's a group. It inherits a ring structure through Minkowski sum. And that group, that ring rather, it turns out is the K-theory ring of the toric variety. The polytopes that I was giving in my example are isomorphic with the classes of the corresponding line bundles under this isomorphism. So if you're used to working with polytopes, Minkowski sums, subdivisions like this, you've been working in toric K-theory all along. Good. So, the matroids and the delta-matroids that I introduced earlier are examples of polytopes that are compatible with certain fans that come from these root systems. You know, whether I'm looking at type A or type B, I look at the hyperplane arrangement with determined by the root system. And, well, if my condition that all edges are in root directions mean that all edges are normal to these hyperplanes, which says that the polytopes have normal fan coarsening these fans. So the polytopes are compatible with these two fans. So when I'm working with matroids, I am working in this type A toric variety that I already mentioned for this fan sigma sub an minus 1. When I'm working with delta matroids, I'm working in this fan sigma bn. And there's a name which I've included on this slide for the set of all polyhedra which are compatible with these fans. These are called generalized permutahedra. So these were introduced more or less by Edmonds in 1970. They've had lots of appearances in optimization. Postnikov in 2008 wrote a combinatorial masterwork on type A generalized permutahedra. These are just the polytopes that show up normal to these two fans, so that show up in the K ring of these two toric varieties. Okay. So these are the first of the theorems from this paper I'm talking about, although you see I haven't attributed either of them to the paper because both of them have near precedents before, and we just had to make a mild adjustment to deal with the translation invariance that comes up in this K-ring. But in any case, we can give a basis for the K-ring, right? I defined the K-ring as a certain, as a polytope algebra generated by polytopes, but there are lots of relations between them, linear relations that come from subdivisions, like the one I showed you, and other relations that come from translation. So, given that presentation, a basis is not completely obvious, but you can give nice bases. You can choose a set of polytopes that give you a basis for these rings. So here's how that's done. It is, you use Schubert matroids or Schubert delta matroids, the case may be. This name Schubert is an algebrogeometrically motivated name because these are all representable, and the representations come from the Schubert stratification of the Grassmannian or the orthogonal Grassmannian, as the case may be. In type A, if you take a Schubert cell in the Grassmannian, pick a cell, pick a generic point in that cell, it will be a representation of this Schubert matroid. The definition I've written down is the geometric one. You take a cone in your fan, you take its dual, translate it, and intersect that with the cube. That achieves the same thing. And so this gives you a nice combinatorially tractable basis as a group for these K-rings. These are statements of combinatorial interest because a map from the K-ring is what is known as a valuation. And people are interested in valuations on matroids and on delta matroids because a lot of the invariants people care about, like the top polynomial, turn out to be valuations in this sense. So we can give a nice basis for this ring. But all right. The thing I promised in the title, sorry, go ahead.
Quick question. When you're dualizing this cone, no? So you're actually in the dual space. So maybe you have to you're identifying this the Rn with its dual there. I mean
I was in the dual space all along. When I defined these fans, I was in the dual space. So I went back to the primal space.
Okay, and the sigma is some arbitrary. What is that? Oh, that's an element in the fan. Okay.
That is a cone of the fan. Sigma is any cone of the fan.
The cone.
Yeah. I defined these fans as living in the dual space. So now this goes back to the primal space.
Oh, okay. Thank you.
Thank you. Thank you for keeping me honest. I'm glad for the questions. Keep them coming. All right. So yes, as I was saying, what I want to do is relate the polytope algebra to tropical intersection theory. As I said, the polytope algebra by Morelli's theorem is K-theory of toric varieties. Tropical intersection is Chow cohomology of toric varieties. And how can we pass between them? Well, there is a classical answer to this, which is the Hirzebruch-Riemann-Roch theorem, which I've written down here. It says, in fact, for any smooth quasi-projective variety X, there is an isomorphism between these two rings, the K ring and the Chow ring, once I tensor by Q. And the isomorphism sends a line bundle to the exponential its Chern class. Moreover, there's a commutative triangle down here, which you can read as saying, if I want to do a computation in K-theory and get a number, probably my computation is the Euler characteristic of some class. That's a nice way to get numbers. I push to a point in K-theory functorially. If I want to get a number in the Chow ring, probably I end by integrating something, pushing to a point. And the Hirzebruch-Riemann-Roch theorem says how to make these things commute. You have to multiply by a Todd class on one side. So, I mean, general powerful theorem, a little bit tricky to use for combinatorial purposes. One reason is that I have to tensor by Q, and I really do get denominators. You know, when I take a line bundle, take its formal exponential, I get, 1 over some sum of 1 over n factorial times C1 to the n. And these quotients are something that you might wish not to have to deal with. The Todd class is also complicated to describe in general. So trying to use the Hirzebruch-Riemann-Roch formula for doing a combinatorial computation brings in the Todd class, and you have to deal with the funny coefficients in the Todd class. So there is a paper by Bergman, Fink, and Seng who did the type A stuff that I'm talking about. And they gave a different isomorphism between the K ring and the Chow ring that cures the two features I just pointed out. First of all, it's over Z. I don't have to tensor by Q anymore. And the analog of the tau, the analog of the Todd class. The analog of the Todd class is an easier thing to deal with. It's just 1 over 1 minus the Chern class of a simplex. That's fairly easy. And the best part is that it relates the matroid polytope to its Bergman fan. This, I think, touches on a question that was asked earlier, right? I have these two things associated to a matroid. One is the matroid polytope, and one is the Bergman fan. The Bergman fan is not the whole normal fan of the matroid polytope. It's a well-chosen subfan of the matroid polytope. And there are many nice computations that use the matroid polytope. There are many important computations that use the Bergman fan. It would be nicest to be able to relate those two. Hertzsprung-Riemann-Roch does not. It just turns the polytope into its normal fan. But this thing does, up to twisting by the standard Cremona transform. This isomorphism actually sends the matroid polytope to its Bergman fan. So I like this. I think one way to think about this result is that it says the Bergman fan is actually natural. It's actually a reasonable thing to associate to the matroid polytope. It explains why they have the same additive relations, for instance. It explains why they behave similarly. So this result is kind of a technical tool, but I like it for its own sake as explaining the connection between the polytopes and the tropical intersection theory.
So it seems more like a specialization of Hilbert-Riemann-Roch, but probably one has to do quite a bit of work to make it explicit. Is that the way they prove it? They use Hilbert-Riemann-Roch. Is that right?
They do not prove it using Hertzsprung-Riemann-Roch. It is a replacement, okay. not a special case. They prove it by using this Goreski-Kottwitz-McPherson theory by equivariant localization. Just kind of, you can bash it out by hand, right? You can represent this K ring and this Chow ring both using localization as collections of local data.
Okay.
And at that level, it's not so hard to say what the map is. You take a torus character on the K side and you add 1 to it. And so you substitute Ti with 1 plus Ti. And in the localization description, that's what the map is. And then you check that it's an isomorphism and that the triangle commutes directly using these localization computations. So yeah, it's a replacement rather than a derivative of Hertzsprung-Riemann-Roch. So it's kind of surprising, right? A new isomorphism. And this particular toric variety has an extra exceptional isomorphism. So that is from this archive paper of Birgit, Yer, Fink, and Seng in type A. And our paper, to appear, has the counterpart in type B. So it's a similar kind of thing, right? Not a derivative of Hertzsprung-Riemann-Roch, but a replacement. You do a game with localization, slightly more complicated in this case. You have to make a different replacement in one where xi is positive than where it's negative. But it gives you a way to replace the Todd class with something easier, avoid the denominators in Hertzsprung-Riemann-Roch. It's Weyl equivariant, so it gives you a combinatorially better behaved or easier to work with map between these two rings. So if you have a polytope computation and want to turn it into a tropical intersection computation, this is a simpler way to do it. Now, like I say, I think the most interesting part of this type A exceptional isomorphism is this fact that it turns the matroid polytope. Well, okay, I've written it as the class of the divisor. That's an element of the K ring, but it's the matroid polytope. It turns the matroid polytope into its Bergman fan. It kind of shows where the Bergman fan come from. It justifies the Bergman fan. So is there some version of that in type B? Well, partly. If I have an independent set polytope of a matroid, remember this is one of the examples of delta matroids I listed. So if I have one of these special delta matroids that comes from a matroid as its independent set polytope, then our map does a very similar thing. It turns the independent set polytope into a version of the Bergman fan, the augmented Bergman fan, which appeared in this 5-author paper. And what is the augmented Bergman fan? Well, it's like the Bergman fan, except instead of the Bergman fan with the tropicalization of a linear space, the augmented Bergman fan is the tropicalization of an affine space. You take an affine translate, a generic affine translate of your linear space, tropicalize that, and that's the augmented Bergman fan. That's not a definition because M might not be representable, but you can write down combinatorially what this affine translate does. You pick certain faces in the normal fan to the independent set polytope, and that is your augmented Bergman fan. So that part of the answer is nice. We have these augmented Bergman fans for certain delta matroids. We wanted an analog of the Bergman fan for all delta matroids, and it turns out we don't quite get that. If I take an arbitrary delta matroid, then I don't get a pure dimensional image under this map. So here's the first example. I take this diagonal in the square I had before. We have this additive relation using the polytopes, right? This diagonal is the sum of the two triangles minus the square. Now the triangles and the square are independent set polytopes up to the Weil group action. So the first triangle is an independent set polytope. The second one is a reflection of it. And the square is an independent set polytope. And now I have a one-dimensional thing minus a two-dimensional thing. So it's not a pure dimensional class. So that's, a halfway nice result. We don't get a Bergman fan analog for every delta matroid, but at least some of them have nice fans. Okay, what can we do with this apparatus? Well, I wanted to show off one result that we can get, which is to compute the volume polynomial for our toric varieties. So we have these two toric varieties, the type A Cox-Litter arrangement fan and the type B Cox-Litter arrangement fan. And we'd like to write down the volume polynomial. We'd like to write down a polynomial, right, that answers the question, given a collection of divisors, what is the intersection product of all these divisors? So in order to do this, the first thing we should do is give a basis for the Picard group, give a way to express your divisor in terms of a sum of some fixed chosen basis of divisors, and translated back to polyhedral language. That's what I have on the slide here. So sum of divisors, that is tensor product of line bundles, that's Minkowski sum. So what I'm asking is, if I have an arbitrary polytope that goes with my fan, so that's a generalized permutahedron, how can I write it as a Minkowski sum of a fixed set of polytopes? So in type A, there's this nice theorem, Detour, Dilla, Benedetti, and Doker that shows how to do this. You can use the standard simplex with n vertices and all of its faces. Every matroid and every generalized permuthedron, more generally, is uniquely a signed Minkowski sum of faces of the standard simplex. So this has a type B analog, as we prove in our paper in progress. You use now simplices, including the origin as well. And there are reflections in some number of the coordinate hyperplanes, so I can use negative instead of positive standard basis vectors in some of them. And then I have a similar statement about that collection of simplices. Every delta matroid, and more generally, every type B generalized permutahedron is a Minkowski sum of these in at least one, in exactly one way.
But Alex, didn't you allow a genuine polyhedra in this in these GPs? So your polyhedra need not be bounded, right? GP should.
I should say bounded. Yes, sorry, I did say bounded. So if I didn't say that in the definition, I should have said bounded here. So
okay.
Yes, these theorems should include the boundedness assumption. Thank you.
All
Good
right.
point.
Okay. Thank you.
Thanks. Okay, so these are bounded. And right, they're bounded. I want to compute their volume. The volume polynomial, the Bernstein-Kushner-Renko theorem says I can, computing these intersections of divisors is computing volumes or mixed volumes of these polyhedra. They should be bounded. Okay, so how do I do that? Well, again, here's a type A theorem, classical combinatorics, and its type B counterpart due to us. That says, well, if we want to compute the intersection of these divisors or the volume of a polytope, we express it in the basis given by the previous slides. We express it as a sum and difference of simplices. Then we need to compute the mixed volume of these simplices. We need to intersect the divisors corresponding to these simplices. So Alex Postnikov did this in type A, not using the toric language. It can be reproved using the toric language, but he says, what's the mixed volume set of simplices? What's the intersection of these divisors? Well, it's 0 or 1, and you can tell which one it is by looking at transversals in the Hall-Rados theorem sense. The simplices are indexed by sets, S1 through Sn minus 1. And if I choose any element, delete that element from all the sets, and the remaining system of sets has a transversal, meaning I can pick a different element from each set, then the intersection is 1, otherwise it's 0. We get something very similar in type B. It's not 0, 1 anymore, but it's again to do with counting transversals this time. So we just count transversals of the system of sets indexing our divisors that are admissible in the sense I gave before. They don't have both I and I bar in them. So just to restate this in terms of intersections, Postnikov's theorem is about intersections of linear spaces. If I have a collection of linear spaces, hyperplanes, if I have a collection of hyperplanes, and I know their supports, I know their matroids, do these hyperplanes generically have an intersection or not? That's what the condition is here. If they do intersect, they intersect in 1 point, so that's why Postnikov's numbers are 0 and 1. In type B, what are you doing? You are taking your linear hyperplanes and inverting some of the coordinates. Replacing EI with negative EI corresponds to replacing X with 1 over X. So if you take a hyperplane, take the reciprocal of some of the coordinates, do this possibly with different coordinates for each hyperplane, this theorem tells you what the expected number of intersection points is. So these are semi-inverted linear equations, which were studied in this paper of Schulten and Vincent in 2019. So we can give a solution account of the number of solutions for a generic system of these semi-inverted linear equations. All right. Last of all, I mentioned this Matroid Chow ring near the start. What's exciting about the Matroid Chow ring is that you can use some geometric inequalities that come from Hodge theory. And I want to show you the tools we use to do that in our setting. So that are these Matroid tautological bundles. How does this work? let's say I've got a matroid. Let's say it's representable. So I have a linear space that corresponds to it too. Well, that linear space V corresponds to a point in the Grassmannian. And I can take its torus orbit. And if I take the closure of that orbit, I get the toric variety of the matroid polytope. So now this is this XM. This is the complete toric variety that you asked about before. This is not the matroid variety that Bergman found, but it's the projective thing that corresponds to the polytope. That toric variety embeds in the Grassmannian, and so now I can resolve it to the toric variety of my type A fan and use that to pull back a line bundle, like the quotient bundle or the subbundle. It's more useful to use the dual of the subbundle. I pull that back and I get these bundles on my toric variety for the type A n-1 fan. That construction assumed there was this linear space V, but if there's not, you don't get a vector bundle, but you do get a K class of a vector bundle, again, by doing the local imitation of this construction. That is also from this paper of Bergman, Ayyer, Fink, and Seng. And a counterpart exists in type B. In fact, there's a few different sort of ways that you might want to embed your type B toric variety into some kind of Grassmannian, and a few different kinds of bundles that you can pull back. So realizable matroids give you bundles. Non-realizable matroids give you K classes that don't quite correspond to bundles, but have local information that is compatible with being a vector bundle. Now, what's nice about these is that we can use the Hodge package that I mentioned on the 4th slide to get inequalities. So I've written down here the kinds of inequalities that you get from Hodge theory. The classical inequality that you get, well, one example of one of the classical inequalities you get is this Khovansky-Tessier inequality that I've written down here. If I have two classes alpha and beta that are Neff divisor classes, then alpha times beta squared times some fixed class. Alpha times beta times a fixed class squared is greater than alpha squared times that fixed class times beta squared times that fixed class. So this is a log concavity statement for the sequence of powers alpha squared, alpha beta, beta squared. In fact, there is this work of Junha and Peter Brendane, which says volume polynomials have not just this Khovansky-Tessier log concavity property, but this kind of works in two classes at a time, this Khovansky-Tessier inequality, and you can generalize it to giving properties of the whole intersection volume polynomial that looks at just more than two classes at a time. This is the Lorentzianity property. I won't define it here, but it's the right generalization of these inequalities. And in type A, the bundles that I wrote down on the previous slide, their Chern classes satisfy these inequalities. So you can use them to produce, to prove combinatorial theorems like the ones inequalities on matroid invariants. In type B, so I've said how this is done. Given that my time is running short, I think I will jump to what happens in type B. And in type B, it's a bit awkward. In type B, we can prove inequalities. You can use this Hodge package given a technical assumption that there's a matroid which projects onto the delta-matroid in the way described on this slide. We call this an enveloping matroid. This is a term from the book of Borovit, Gelfand, and White. We need there to be a matroid polytope whose image under subtracting pairs of coordinates is the given delta matroid, roughly because there are tools for getting this Hodge package for matroids, and we use localization computations to project them to delta-matroids, and we need this projection to exist for the localization to work out right. So seeing that I'm out of time, I'll just say briefly, these exist often. We don't know if they exist for every delta-matroid, but they exist for a lot of the cases we care about. And if they exist, we can prove positivity results, like the ones that the matroid Hodge theory proves. I think that's a good place to stop. So thank you.
Let's thank Alex for a wonderful talk. Questions, comments? I had a question. So the K theory, you gave this purely combinatorial description using polytopes. So that's the K0. Is there a way to talk about higher K theory using just polytopes?
Yeah, this is the K0. I don't know. Yeah, I mean, I'd be interested if there were, but I haven't seen very much treatment of K1 or higher K theory in these combinatorial computations at all. So I'm not sure.
And the Chow ring, is there a description of that?
Oh yes, I left that out of the slides because I thought that might be familiar to this audience, but maybe I shouldn't have done this. The description of the Chow ring is given by tropical intersection theory. So you could say that classes in the Chow ring correspond to a star of the toric variety of sigma is the set of balanced Minkowski weights, right? Balanced subfans of sigma with balanced weights, and the intersection product is the tropical intersection product. So if I have two fans, then I take one of them, I use this fan displacement rule and take the stable intersection. That gives you the Chow ring of the toric variety.
I see. Great. Thank you.
Thanks.
Can I ask one question?
Yeah.
So
Yes.
to define matroids, why did you take the vertices from 0, 1 power n? Can you take any lattice, set of lattice point and define something similar?
Yes. So if you take vertices from 0, 1 to the n, then you get something that looks like sets, right? You get indicator vectors as sets. If you use any vectors, you get, one name for the object you get is a polymatroid. If you throw out the 0, 1 condition, I guess for polymatroids, you want to make this natural numbers to the n. Up to translation, if you have a bounded polytope, I can translate into positive orthant. And yeah, these have similar interpretations to matroids. So for instance, if I have a hyperplane arrangement, I get a matroid. If I have a arrangement of linear subspaces, but they're not all hyperplanes, I get a polymatroid. So yeah, that is an interesting thing to do.
Oh, okay, thank you. Can I ask one simple? So the K theory we consider for the Grassmannian,
Yes.
the algebraic K theory or complex K theory?
Yeah, algebraic K theory. Sorry, I should have said that. This is K theory of algebraic vector bundles, although I guess you could do it in topological K theory. I suspect it would come out the same, but these are K theory of algebraic vector bundles.
Okay, thank you.
Can you please shed light on some tropical aspects of this? So for instance, matroids are essentially tropical linear spaces. And so is there a corresponding interpretation for these delta matroids and also the other results and the results that you showed? about delta-matroids, the positivity results and so on. So is there a tropical interpretation, or how does it relate to the tropical picture?
It's difficult to give the tropical interpretation because, I mean, I guess this paper of Felipe sought to the tropical interpretation, and okay, so there are the, you can take, I can tropicalize an isotropic subspace. As I say, that doesn't quite, that gives me more information than the delta matroid. But if I take this tropicalization and I look at only certain of the strata in tropical projective space, the admissible strata, the ones that correspond to admissible sets, then I get a tropical object that corresponds to a delta matroid. So I mean, it's a funny thing. It lives far into the boundary of 2n dimensional tropical projective space, but it is there. So
and then is there a way to translate these results, the positivity results and so on, in tropical language, or what do they mean in the tropical world?
Yeah. Well, okay. So they mean, I mean, I suppose what these results say, I mean, especially these kind of, I guess what the results say is that in principle, yes. And so if you have an invariant you care about, I skipped the slide where I actually, defined an invariant, for instance, but here's a function of delta matroids, the interlaced polynomial, which people care about. It came from, I think, applications to DNA sequencing, but it counts decompositions of graphs into 1-in, 1-out graphs into 2 cycles or something like this. And so, the kind of thing that this says in principle you could do is give a tropical way to compute this. For instance, if you like these Chern, Schwartz, McPherson classes of matroids, there are these results that say, oh, you can compute the Tut polynomial using that. You can compute the David Spires G invariant using that. And so sort of in principle, you could do these computations for delta matroids as well in tropical intersection theory.
Okay. Yeah, and also even just stepping back to the usual matroids case. So for instance, the Matroid Chow ring, so that has a tropical interpretation, is it? Does it have a tropical interpretation?
Yes, that is the tropical intersection theory as it was defined by, my slide's not, but kind of as it was defined by Rao, is the same ring. I guess this paper of Bachman, Ure, and Simpson kind of sheds light on this, because for every Bergman fan of a matroid quotient of M, you get a class in the Matroid Chow ring of M, and they intersect in the tropical way.
Thank you.
Thank you.
Other questions or comments? The online participants, you can unmute yourselves. AV team, please enable unmuting for the online participants. Or you can type the question in the chat box. Other questions? Comments? Yeah.
Yeah, so in the exceptional HRR case, A-type, what is the map, Jai? Is it the Chan character map?
It is. I've written its description at the bottom here, that it is, I'll highlight it in orange. I mean, the way it was defined is by this localization computation. You change so a torus character defines a vector bundle over a local patch in the algebraic K theory, and it defines a divisor on the Chow side, and you just kind of formally map one to the other. So the reason I like this statement that says a matroid polytope becomes its Bergman fan is that that's a more global characterization of it, right? If I have one of the line bundles that comes from a matroid polytope, Then I send it to the Bergman fan, which is the tropicalization of that linear space if it was a realizable matroid. So that's the closest to a global way that I know how to think of it.
Oh, thanks.
Thanks.
Further questions? If not, let's thank Alex again for a wonderful talk.